Now we've talked about anisotropy, and I've given composites as a particular example in the context of orthotropy to understand why it arises and how it influences material behavior. And the example I gave you was this example. Now, if we go back to this example and remember the type of compliance matrix that we have, there are a few things to comment here. So what we have observed is that when I put different fibers in every direction, then I end up having a particular anisotropic structure forming. Now that particular structure is influenced by the so-called microstructure of the material. In other words, typically, and I'm going to show you some examples shortly, as I in fact already mentioned, the fibers are very, very small in diameter with respect to dimensions of the structure. You could be making a wing of an airplane that's of the order of meters, but the fibers are of the order of micrometers. So there is a 6 order of magnitude difference, a millionfold difference in the dimension. And so the dimension of the fibers lies in a micrometer range. It's called the microstructure as a suitable, let me say, terminology. And this is the microstructure, and that microstructure is responsible for the form of the compliance matrix. Now, here we have this orthotropic material because every fiber had a different material property. Now, but it turns out something strange could happen. So, for instance, if I had picked every fiber to be of the same type, so all of them are, say, carbon, okay, or glass or Kevlar, it doesn't matter. Let's pick carbon. So all of them are red. And so red along that direction, and that direction. So when you look at the structure and these pictures eventually, and remember the discussion, you can deduce that the shear moduli are all going to be different in general, but in this particular case, when the fibers are the same and carbon, they're just going to be the same. One shear modulus associated with every plane. One Poisson ratio associated with all, and 1 Young's modulus associated with all. So there's going to be only 1 over E's, 1 over G's, and minus nu over E's. Does that mean that this material is then isotropic? We understand that it's not isotropic because if I pull along a fiber direction, the material is going to be strong, but if I pull along another direction, you can imagine that it's not going to be as strong. So, and in the context of elasticity, it's not going to be as stiff or compliant. So, well, therefore, it seems to have the form of a isotropic material, but it's not isotropic. So the only thing it can be is cubic, right? So in other words, E and nu, they are independent parameters, but so is G. It's not related to E and nu through the usual relation. So therefore, the exact choice of fibers that you put in, they influence the outcome of this structure significantly. And in fact, you don't have to always put in something into a matrix, in this case epoxy, to influence the outcome, the behavior, mechanical behavior of the composite. What you can do is, on the contrary, extract something. So here is an example to that. So now I want to show you some examples to things that would fall in the context of composites, at least with respect to the mechanical analysis. So this is a aluminum foam. So it's solid. It is made of aluminum, but its properties are not the same as the properties of aluminum. This can be isotropic, but nevertheless doesn't mean it's anisotropic. But nevertheless, the properties are different from the properties of aluminum because the solid part behaves like aluminum, but when I put so many voids, I sort of weaken the structure and end up with a different structure, a different mechanical behavior, which finds its own uses in, for instance, energy absorption, which could be mechanical like impact, or sound absorption, etc. So you can alter the overall mechanical behavior of a material by playing with its microstructure, by putting in this case, for instance, not additional material, but actually extracting material from it. The way this is manufactured, as the name suggests, is aluminum foam. It's done in a clever way to achieve this final outcome, but ultimately the types of methods that you use to determine the material properties of this, let me say, composite or porous material, another name is cellular material, they are the methods of composites. Okay, so you use the methods of composites to find those material properties. Now, of course, the material properties might in general change as you change the size or the volume fraction of the pores. This is the same aluminum foam, but now with a smaller size of the pore, possibly a different ratio of the pores as well with respect to the overall volume fraction. So you don't always change material properties by adding something, but you can also extract. In this case, the overall properties are most likely almost isotropic. But now we've talked about composite materials that are associated with fibers. And here is a carbon fiber composite plate. The fibers are sort of running along that and that direction. So this is very close to being the orthotropic 2D plate that I provided, except that now we have fibers running along two directions. So the Young's modulus along both directions are very, very high. And so you see that the epoxy is typically black, and the fibers, the carbon fibers, they're also quite black actually. So now you have a strong plate that is a combination of a polymeric material and carbon fibers. Now, not every structure is flat, so sometimes you want to form them into more complicated shapes. A simple shape that you can make is a tube. Here's a carbon fiber tube, right? It's hollow in the center. And now, why would you like to build something out of composite? Because the idea is if you would like to achieve the same strength and modulus with, say, steel, it would be heavier. So if you want to do something that is lightweight, carbon fiber composite, for instance, could be a good choice. And this is at least a structure that's slightly more complicated with respect to geometry than a plate. And then what you can do is you can take two carbon fiber plates, and in between you can put in Kevlar. And here you see Kevlar threads coming out. It's very much like just usual textile thread, and it's sandwiched in between to give it additional strength. Right? So the overall properties of this one would be different than the properties of only carbon fiber plate. And again, going back, you don't always add something to the material to alter its material properties. This is a sample that we have discussed before. You make a cellular material. Here, the material is polymer. It is almost isotropic, okay? But here, it is porous. And in fact, it's porous such that the Poisson ratio of this part is close to being 0.5. It's incompressible. This is 3D printed. I assume that the infill ratio, if it were 100%, then it would be 0.5. But here, there are pores, and though that induces the Poisson ratio to be drastically different, in fact, even negative. So here is 0.5, close to being incompressible, and here it's negative, a huge difference that arises from the microstructure of the material, or the 3D printed structure of the material. So that's the way the microstructure, the internal ingredients, and the way they are arranged arises in the characterization or influences the mechanical behavior of the structure. And anisotropy, general anisotropic behavior, is how we characterize that mechanical behavior.